In this video, we're going to look at an example problem that's related to hydrostatics. In this problem, we have a 280 kilogram rectangular gate that is 6 meters wide. That 6 meter dimension is into the page. This gate is hinged at point B right here, and it contacts the floor at an angle of 45 degrees with respect to horizontal. Water is contained or held back by this gate. And what we are to do is to determine the minimum force that will be required to open the gate. In this video, I'm going to mimic the problem-solving process that you should employ in your homework problems. The first thing that we should do is we should restate the problem and what we're trying to find. So here we have a rectangular gate that's submerged in water and it rests against the floor at a 45-degree angle. And we are to determine the minimum force that's required to open the gate. This is just a restatement of the problem that I just read. The next thing that we need to get in the habit of doing is drawing a sketch. And here I have redrawn this sketch. Also, I have indicated that we are going to need to know for this problem solving method the distance that is in the plane of the plane surface, or in the plane of the gate. And we're going to need to know that distance from the free surface of the water right here. In addition to that, I've stated what I know. I know that the fluid is water, and we know or can approximate the density of water as being 1,000 kilograms per cubic meter. We know that the gate mass was specified to be 280 kilograms. And we know that the gate is 6 meters wide into the page dimension. Also, we should get in the habit of stating our assumptions. In this problem, we are going to assume, because of the way that it's drawn and the way that it was presented, that atmospheric pressure is going to act on both sides of the gate. It's going to act above the water as well as on this side of the gate. So when we do our calculations, we're really going to be working with gauge pressure. We don't really need to worry about the atmospheric pressure or absolute pressures. Also, we're going to make the assumption that the density of the fluid remains constant with the depth. We're not going a significant distance here. We're going 3.5 meters. So the water is not going to change its density significantly, and we're not told anything otherwise that would make us assume or would disallow this assumption. Also, when we get to calculating the force that's required, we're going to make an assumption that the hinge friction right here at point B is negligible. So, after we've made our sketch, we've identified our knowns and our assumptions, we need to lay out an approach to this problem. In class, we've talked about an approach for determining the force, or the force due to pressure acting on a planar surface. And that approach is as follows. We first need to find the magnitude of the force that acts at the centroid of the plane surface. This magnitude, however, does not act actually at the centroid. The line of action of the force that results from the pressure acts at the center of pressure. So we need to find this line of action of the force due to the water pressure, and that is going to lie at this point called the center of pressure, which we will need to calculate. After we've determined the force that is exerted by the water, we're going to need to perform a static analysis of the gate to determine the minimum force that is required to cause this gate to open. The first thing that we need to do is we need to find the magnitude of the force due to the hydrostatic pressure. And from our studies, we know that we can find the magnitude of the force by determining the pressure that acts at the centroid, or at the center of this plate. In the problem statement, we're given that the height above the gate hinge is 1/2 meter. And we also know that the gate from the hinge down to the bottom is 3 meters. Since we know that this acts at a 45, or this rests at a 45-degree angle, we can use similar triangles. We know that the centroid is going to be right in the middle of this gate. And we can use similar triangles to say that the depth down to from the hinge down to the middle of the gate is going to be half of this distance, so 1.5 meters. Okay, so if we can calculate the pressure, which we know how to do, down at this point, we can then calculate the force, the magnitude of the force that acts on the gate due to the water. Okay, so the height to the center of the gate, or the depth, I should say, to the center of the gate is going to be 0.5 meters plus the 3 meters divided by 2 gives us a total of 2 meters of depth to the centroid, or the center of the plate. Now, looking forward, we know that when we are going to determine where the center of pressure lies, we're also going to need to know the distance along this tilted axis, along this y-axis to the centroid as well. So in order to find where that centroid is located, or where the center of this gate is located along this tilted y-axis, we can again use some geometry, and we know that the centroid, or center, and along the y direction is going to be equal to the 2 meters of depth divided by the sine of 45 degrees. And when we calculate that out, we're going to get 2.8284 meters. We also know that the pressure at the centroid is given by rho times the gravitational acceleration multiplied by the depth under the water to the centroid. However, we're really interested in finding the force. So we also know that the force magnitude is going to be the pressure at the centroid multiplied by the total area of the gate. And if we substitute in, that's going to give us rho g h sub c times the surface area of the plate. That also means that we need to establish the surface area of the plate. Well, the surface area of the plate is going to be the length of the plate in this direction times the width of the plate, which was given to be 6 meters. So along this tilted direction, since we know that the vertical distance is 3 meters, we can determine the length of, or the total length of the plate as being 3 meters divided by the sine of 45 degrees. And we know that the width, because it was given in the problem statement, is 6 meters. All right? So the resultant force, or the magnitude of the resultant force, is going to be given by the density of water times gravitational acceleration times the height to the centroid multiplied by the length and the width. And when we put that all together, it looks something like this. The density of water is 1,000 kilograms per cubic meter. Gravitational acceleration in the SI system we're going to approximate as being 9.81 meters per second squared. We have a 2 meter depth from the free surface of the water down to the centroid. And then we're going to multiply by our area, which is 3 meters over the sine of 45 degrees times 6 meters. Multiplying all of that out gives us 499,443.7 or so newtons. And we can approximate that, or we can convert that into 499.444 kilonewtons. Of course, it's probably not necessary to carry all of these decimal places, but for the sake of accuracy, when we do our further calculations, we will keep those decimal places. Okay, so this is the magnitude of the force, but the force that is exerted on this plate does not act through the centroid. It acts a little bit lower down, because we know that the pressure and thus the force is going to increase with depth in the fluid. So we need to know where the center of pressure is. All right, so we need to find the center of pressure. Which we will label as Y sub P. And we also know that y sub p, or the location of the center of pressure, is related to the location of the centroid by the following relationship. The y location along this tilted axis in the plane plus the second moment area, the second area moment of inertia, all right, about the centroid, divided by y sub c multiplied by the area over which it acts. Of course, now we need to find the second area moment. And the way that we do that is we know that this has been calculated for a number of different geometries. So what we're going to do is we're going to take a look at some tables that tell us about the different moments and area moments. This is a table from the Fundamentals of Engineering examination handbook. And this is where we're going to find the area moment of inertia. And we see a bunch of different geometries that are located on the left-hand side. The location of the centroid is the second column, and the third column tells us about the area moment of inertia. Since the gate is rectangular, we're going to be looking at this middle column right here, and I'm going to zoom in a little bit on that so that we can take a closer look at this. We're looking for the second area moment, or the moment of inertia, about the x-axis, which is given right here in this table for this rectangular geometry. And this area moment is given, according to this geometry, as b times h cubed divided by 12. All right. Well, we need to keep in mind that this is sort of the top projection of our rectangular gate. So B is going to represent the 6 meters of the width of the gate. So B is equal to what we called W before, which was 6 meters. And the height is going to be the 3 meters divided by the sine of 45 degrees. Using all of this information, now I can find the y location along the tilted axis of where the center of pressure is, or where the force is going to act. So we have the location of the centroid along the y-axis, which we determined earlier. That's 2 meters divided by the sine of 45 degrees, and now I have to plug all of this information in right here. So this will be, for our area moment of inertia, we're going to have 6 meters for B multiplied by the height cubed. So that's 3 meters divided by the sine of 45 degrees. That's going to be cubed. All of that is going to be divided by 12. And then I have to divide that by the location of the centroid along the y-axis again, which is 2 meters divided by the sine of 45 degrees, multiplied by our area, which we determined up here to be 3 meters times the sine of 45 degrees, multiplied by 6 meters. Running through all of those numbers gives us a result of 3.3588 meters. So before, we determined that the location of the centroid along the y-axis, if we traveled from the surface of the water along this 45-degree angle, it would be a length of 2.82 meters, or 2.83 meters. And then moving further down is where the force is actually going to act, and that force action is going to occur 3.36 meters along this plane. Now that I know the magnitude of the force and where it acts, my next step is going to be to apply a static analysis so that I can determine the amount of force that's required to start opening this gate. However, I've determined that we have almost 500 kilonewtons due to the force of the water, due to the hydrostatic force, But that force, we've determined that it acts 3.3536 meters away away from the surface, from the free surface of the water. But to do my static analysis, my hinge starts here at point B, which is located half a meter down in the water. So in order to get my geometries correct, I actually want to subtract this part off of my off of this 3.36 meters measurement, so that I can do my static analysis. So to do that, the distance where the force acts along this gate here below the hinge, it's actually going to act at a distance from the hinge a distance where we take this 3.3588 meters and we subtract this distance, this 45 degree or this in plane distance, and we know that the horizontal distance here is half a meter. So we can use some geometry again to subtract that out. So we want to take 0.5 meters divided by the sine of 45 degrees, subtract that out to get how far down from the hinge along this gate the force acts, and that gives us 2.6517 meters. All right, so we also are going to need to calculate the distance from the hinge to the centroid. So we know from before the centroid was located let's see, sorry, let me write this down. From the hinge to the centroid, we know that the centroid was located along the y-axis at a distance of 3 meters divided by 2, so that's our 1.5 meters, divided by the sine of 45 degrees, because we knew that the centroid, since this was 3 meters down, we knew that it acted, we know that the centroid is halfway down, right, so it's 1.5 meters divided by the sine of 45. And then from that, we also, I'm sorry, that is just going to be the distance to the centroid from the hinge. So that is going to be 2.1213 meters when I calculate that out. With these numbers in hand, now I can proceed to drawing my free body diagram of the gate so that I can perform a static analysis on it. So now I have constructed a free body diagram of this gate, and we know that we have the resulting force from the hydrostatic pressure, or the hydrostatic force of the water above it. We have the weight force, and we are now asked what is the force that's going to be required to open this. What's the minimum force? So we could apply a force from any side along the bottom of this gate, but we know from statics that since we're rotating about this point, we want to generate a large moment, or the best way to generate a moment is going to be further away from the pivot point. So I want to maximize this distance, which is going to be given by 3 divided by the sine of 45, which is the total length here. And this would be where I would have to apply my force in order to use the minimum amount of force to open the gate. From this free body diagram, we also know that we could sum the forces, the sum of the forces in the x direction, because we're just going to start to overcome equilibrium here in order to open the gate. The sum of the forces in the x direction must be 0, and the sum of the forces in the y direction must be 0. But we don't know anything about the reactions up here either. We could figure them out, but that's not our objective. Our primary objective is to determine the force. So what we're going to work with here is the moment. We're going to sum the moments about point B, and we know that the moments about point B must be equal to 0. Now looking at my free body diagram here, I can say that the moment generated by the force resulting from the hydrostatic pressure is equal to Fr times the distance to the location of that where the force acts if we sum about point B. So that's going to be our 2.6517 meters. All right, we also know that we have a moment due to the weight force, and the weight force is given by the mass of the gate times the gravitational acceleration multiplied by the sine of 45 degrees, because we're only interested in what acts perpendicular or out of the perpendicular to where we're generating the moment. And the distance which that acts at is this distance from the centroid, because that's where the weight force is going to act. So that's 2.1213 meters. Right. And then the other force that we are going to have to contend with is this applied force. Right? And that's going to act in the opposite direction. And that applied force, we know that the vertical distance here is 3 meters. So the total length of this gate, if we were to apply the force at the very end, would be 3 meters divided by the sine of 45 degrees. Of course, what we want to do, since we know what the force is from the hydrostatic pressure, we want to solve for the applied force that's required. So rearranging the equation, we find that F applied must be equal to the force resulting from the hydrostatic pressure times 2.6517 meters plus mg sine 45 degrees times 2.1213 meters. And we're going to have to divide that by 3 meters divided by the sine of 45 degrees, which is the distance at which the force acts. When I put all of my numbers in here that correspond to the mass of the gate, the force resulting from the hydrostatic pressures, and solve for the applied force, I'm going to wind up with 312.865 kilonewtons. So what we can say is that the minimum force required to open the gate is about 313 kilonewtons applied at the bottom of the gate. And in that manner, we have shown why this is the case and why this is the minimum force that needs to be applied, and how all of the other forces interact.